We're on chapter 9. I started chapter 9 last time, well, last Monday, more than a week ago. And what we started talking about are molecular orbitals. And one of the things that I showed you is I described how two hydrogen atoms can come together from infinitely far away, and their orbitals can overlap and they can make a bond. When atoms come together to form molecules, one way that we have of describing the result is molecular orbitals or molecular orbital theory. And the basic idea is really pretty straightforward. In molecular orbital theory, what we say, or the way we describe it, is we describe the atomic orbitals, and you guys already know what atomic orbitals are. They're things like a 1s, or a 2s, or a 2p, right, or a 3s, and so on. Those are atomic orbitals. They're the orbitals that are localized on the atoms, and you know what they look like because we've seen pictures of representations of them. What they do is they combine and they form kind of a hybrid, or and that the difference is an atomic orbital, it's localized on an atom. It's a 2p orbital on a carbon atom is localized, it's centered on the carbon atom, and it stays right there on the carbon atom. When you take atomic orbitals and you mix them together, hybridize them, well, I don't want to use the word hybrid because that's going to mean something else. You combine them to make molecular orbitals. The resulting molecular orbitals are spread out over the entire molecule. And what that does is that allows the electrons to reside over the entire molecule, to exist over the entire molecule. Now, we're only really going to talk about molecular orbitals for just a few molecules. We're only going to look at the first row and the second row of the periodic table, and we're only going to combine two atoms at a time. So we're only going to look at first and second row diatomic molecules. Pretty simple stuff. Starting with hydrogen. The only atomic orbital that's occupied in the ground state of a hydrogen atom is the 1s orbital, 1 electron. So if we have those two hydrogen atoms, this hydrogen 1s, and we bring those atoms together and those orbitals overlap, combine, and make molecular orbitals. The result is that there are two molecular orbitals. Take these two atomic orbitals, one from each hydrogen atom that are coming together, combine them, and we get two molecular orbitals. Right? This is supposed to be a Greek letter sigma. It's a sigma 1s molecular orbital. This is also supposed to be a sigma star 1s. The stars represent what we call anti-bonding. represents what we call a bonding molecular orbital. And in this picture, in this diagram, energy is increasing upward. So one of the important things to understand about this is that the energy of an electron in a hydrogen 1s atomic orbital is higher than the energy of an electron in a sigma 1s molecular orbital that's formed when there's two hydrogen atoms overlap. Yet it's lower in energy than a sigma star, an anti-bonding 1s orbital is formed. So what we do, do you guys understand this picture? The lines represent orbitals. Each line, just like we did with the atomic orbitals, 1s, 2s, 2p. Each line represents an orbital. And that means each line can hold at most 2 electrons. Each orbital can. That part okay? The electrons are represented by the arrows. And we have all of the same rules that we had with atomic orbitals. That is the Pauli exclusion principle. You guys remember which one that is? What does the Pauli exclusion principle say? In your own words. Yeah, each orbital can hold no more than 2 electrons, basically, right? So in other words, in this picture, we can't have more than 2 arrows on a single line, just like we did with the atomic orbitals. The Aufbau, or building up principle, you remember what that is? What that says is that electrons, I mean, you know this, electrons go into the lowest energy orbital that has room. Right? You know that, right? You should know the name. Same idea. That when we have electrons, when we're putting electrons into degenerate orbitals, that means orbitals with the same energy. Hund's rule is the one that tells us we have to put 1 electron in each first. Do you guys remember that? And also, when we're putting those electrons in, they all have to have the same spin. They have to point in the same direction before we start pairing them up. You guys remember that rule? Well, it's called Hund's rule, but as long as you know how to apply it, that's really the important thing. So all of those rules, they still apply to molecular orbitals, just like they do to atomic orbitals. It's the same idea. So what we do is this picture is trying to describe not necessarily the shapes. So I'll try to give you an idea of the shapes in a minute, but the energies, the relative energies of molecular orbitals compared to atomic orbitals. And electrons, okay, where are those electrons? That's one of the important things, is where the electrons are. So the way we do it is we start out with the electrons on the individual atoms in the atomic orbitals, and then we take them and we put them into the molecular orbitals once they form. So those 2 atoms now are close enough together to where the molecular orbitals have formed. Okay. We have the same number of electrons. We started with 1 electron here, 1 electron there. 2 electrons. We put them into the molecular orbitals now using all those rules. So where should they go? The bottom, right? There's 2 electrons. They can both go in there as long as they have opposite spins, right? And this picture, this sort of picture is called a molecular orbital energy level diagram. And it tells us where the electrons are in molecular orbitals in this molecule. The picture is this. You guys know what a 1s orbital looks like. What's the shape of a 1s orbital?
Sphere.
It's a sphere, right? So not a very good sphere, but something like that. That would be an atomic hydrogen 1s orbital. The electron that's in there would, occupy this region of space. And the other hydrogen atom would be the same. When they come together, when they overlap, they form a molecular orbital which looks something like that. It just, this is a nucleus and this is a nucleus, right? That's from one of the hydrogen atoms, this is the other. And the molecular orbital encompasses the entire molecule. And those two electrons that are in there they occupy that whole volume. Is that making sense? I mean, do you at least understand the picture? The anti-bonding molecular orbital would look something like this. It would have two parts to it. It's one orbital, right? And they're not really spherical, they're more like flat here. One orbital, right? And electrons can occupy it, right? There can be an electron in there and it would occupy that region of space. But, it's more like nuclei are more like there. This plane between them is called a nodal plane. And one way of looking at that is to realize that this nucleus has a positive charge on it. So does that, right? If there's no electron density, because the orbital isn't between these two nuclei, those nuclei are going to repel each other by Coulomb's law, right? So that raises its energies. It's higher in energy. It's an anti-bonding orbital. And any electrons that happen to exist in here will take away from the bonding character of the molecule. They're going to make the bond weaker. Okay? We can use the same picture to describe what would happen if we tried to make a helium molecule. This is a hydrogen molecule, two hydrogen atoms. Okay. We've always said, without really justifying it too much, that the noble gases don't really form many molecules. They're hard to make bonds with us, right? We can see why in this picture. We take helium. How many electrons does each helium atom come with? Two. Now, so these are the electrons in the atomic orbitals on the individual atoms. And we bring them together and try to make a bond, a molecular orbital. We take two electrons and two electrons, so we have four, right? If we have two in here, that means the other two have to go up into this anti-bonding molecular orbital. They have to be up in here. Every electron that goes into an anti-bonding orbital takes away from the stability because it's higher in energy than the atomic orbitals, right? Electrons would rather be over here than be up here. But the bonding molecular orbitals increase the stability, the bonding character. So what happens is these two electrons would stabilize it because they're in a bonding molecular orbital. These two would take away from the stability. The result is that this is less stable than the electrons just be in the individual atomic orbitals. Overall, this is higher energy, which means it's not going to happen, because in nature, everything, is going to naturally go to the lowest energy state. You guys follow that?
Is it because they're higher energy, or do they just cancel? Because that's how the book described it. I was just...
It's higher, it's energy. It's all about energy.
Okay.
Definitely about energy. But we have a tool, a way of predicting whether or not a molecule exists, at least these simple diatomics. That's called the bond order. Is that what you're talking about?
Yeah. Yeah.
So bond order, it's sort of like formal charge in that it's just really a bookkeeping tool, but it's a useful bookkeeping tool. Calculation is simple. So the bond order is just, what you do is you look at the molecular orbital energy level diagram, count up all the electrons that are in bonding molecular orbitals, and then all the electrons that are in anti-bonding molecular orbitals, subtract the two and divide by 2.
So for the helium diagram,
Yeah.
they have 2 electrons, right?
What's that?
For the helium, each one will have 2 electrons.
Each helium atom came with 2 electrons.
Okay, so it would be 2 s.
Is that? No, 1s2.
1s2, okay.
Yeah. If you get a bond order of 0, what we say is that molecule is too unstable to exist. It would rather, it's lower in energy for those electrons to be on the individual atoms. So if a bond doesn't form, we say that molecular orbital theory predicts that molecule won't exist. And so if we calculate the bond order for helium 2, right? Dihelium, whatever, it would be, it's 0, right? We have 2 bonding electrons, right? You guys know what I mean by bonding and anti-bonding electrons, right? So 2 bonding and 2 anti-bonding. So molecular orbital theory predicts that dihelium doesn't exist. Okay, so far? Look back at hydrogen. Calculate the bond order. What's the bond order? 1, right? 2 bonding, 0 anti-bonding, 2 over 2 is 1, right? Well, what that tells us is, first of all, that it's predicted to exist. We know it exists. But also, it predicts that the bond is like a single bond, right? You guys know what single, double, triple bonds are, right? So, and we know that that's what hydrogen looks like. What about this one? Guess I could put this one. You guys understand what I'm trying to show there? So what we want to do, okay, so far what we can do is we can fill in the molecular orbital energy level diagram. We can calculate the bond order, and we can predict whether or not molecular orbital theory anyway predicts whether it'll exist or not. So helium comes with 2 electrons, right? Hydrogen comes with 1. Okay. We have 3 electrons, 2 go here, 1 has to go up in that, right? Two bonding electrons, 1 anti-bonding electron. We get a bond order of a half. It's not 0, so at least molecular orbital theory predicts that this molecule could exist. And also, what it says about the bond is that it's half of a single bond, right? What does that mean? It means that it's half the strength of a single bond, hydrogen-hydrogen, a single bond, and that's probably going to be so it's going to be a longer and weaker bond than the hydrogen-hydrogen single bond is. But still, it's not 0, right? So that means it's predicted to exist. You guys see how that works? So bond orders of half or 3 halves are, there's nothing wrong with that.
So you put in the bond first and then anti-bond?
When you're putting the arrows in, you put the electrons in the lowest energy orbital that has room, right?
Yeah.
And the way that they form, okay, so far, we've only talked about the sigma 1s and the sigma star 1s, right? The 2 lowest energy molecular orbitals. What we're going to do now, just a minute, and that only covers the first row, hydrogen, helium. Now we're going to go to the second row. And so, in addition to the 1s, right, we're going to have 2s orbitals and 2 p orbitals overlapping. We're going to make more molecular orbitals, but the rule's the same, right? The lowest energy one that has room gets the electrons until it's full. Is that all right?
Yeah.
Are you guys following this so far? So, a very good picture that will help you is on page 278, figure 9.13. They don't show the other one that you need to know. I'm going to show it to you in just a second. Let's look at this first. Oh, by the way, before we do that, there's one other thing that we can also say about these molecules that we've talked about so far, and that I can ask you, and that is whether or not these molecules are what we call paramagnetic or diamagnetic. define these first. The molecule is diamagnetic, or any species is diamagnetic, then all of the electrons are paired up. There's 2 in every orbital. And what happens is when you put that species, that molecule or that atom, into an external magnetic field, 2 poles of a big magnet, and it's slightly repelled by that magnetic field. What's going on here is that do you remember when we were talking about the quantum numbers, right? N, L, M sub L, and M sub S? Remember those? And when we got to M sub S, I called that the spin quantum number. And one of the things I told you is that the electron's not really spinning, but it acts as if it's spinning. But one of the things that it does that acts as if it's spinning is whenever you have an electric charge, something that's electrically charged that's spinning, it creates a magnetic field perpendicular to the direction of its spin. And that means it acts like a little magnet. You guys buy that? And so if we have 2 electrons in the same orbital, one spinning this way, the other spinning this way, the magnetic fields that are created effectively cancel each other out. You guys buy that? And so overall, it's the magnetic effect is it cancels out. If you have at least one electron that's not paired, then its magnetic field isn't canceled out, and the whole thing, the whole molecule or atom or whatever it is, feels that effect and acts like a magnet. And so it's going to be attracted towards one side of the magnetic field. You guys buy that? Yeah, is that kind of okay? So diamagnetic means they're all paired up, all the magnetic fields of the electrons cancel. Paramagnetic means there's at least one unpaired electron, and that means the whole thing's going to act like it's a little bar magnet. So when we look at the molecular orbital diagram for this molecule, we see one unpaired electron, so we predict that this molecule would be paramagnetic. What about the hydrogen molecule, H2? Is that paramagnetic or diamagnetic? Diamagnetic because it had 2 electrons here, both paired up. Right? And, well, the helium molecule doesn't exist. Those definitions okay? So all you have to do, if I ask you, if one of the questions on the exam is this some specific molecule, and it's just going to be a diatomic, second row or first row, is it paramagnetic or diamagnetic? Right? Then all you do is you fill in the molecular orbital energy level diagram. And that's really what you're going to do, because there's only 2 diagrams really that you're going to have to know. You just memorize them and fill them in. Fill them in, See if you have any unpaired electrons. If you do, it's paramagnetic. If you don't, it's diamagnetic. Now let's go to the second row of the periodic table. We're still talking about diatomics. So there's only two atoms, a set of atomic orbitals from this atom, a set of atomic orbitals from this atom. The 1s orbitals still overlap. You have the sigma 1s and sigma 1s star down there somewhere. On top of that is what I'm going to draw now. Now you have the 2s orbitals overlapping and 2p orbitals overlapping. Okay. So that's a total of 4 orbitals from each atom, right? Before I draw anything. Remember in hydrogen and helium, we had 1 orbital from each atom, and we had, so 2 orbitals, we had 2 molecular orbitals. We're going to have 4 orbitals from each atom, which means we have 8 atomic orbitals. We're going to make 8 molecular orbitals, just from the n equals 2 energy level, 2s and 2p. And they look like this. This is figure 9.13 on page 278. I always remember it. This is the important part. Maybe I think I'll put the atomic orbitals on the side in a minute just to show you where these molecular orbitals came from, but this is the important thing. This is figure 9.13. So these are the sigma 1s and sigma star 1s from the 2 1s orbitals, right? The rest of them, 1, 2, 3, 4, 5, 6, 7, 8, are those 8 that I mentioned. These two come from the overlap of a 2s orbital on each of the atoms, 1 atom on each side, right? These come from the 2px and the 2py. Right? And 2px and 2px, 2py, what have you. There's the 2px on each one, there's a 2py on each one. That's 4, 1, 2, 3, 4. And then 2pz, that's the one that's overlapping kind of in a head-on direction, forms a sigma 2p and sigma star 2p. So, let me show you, then we'll show you again. It's going to look a little more complicated when I put the atomic orbitals in. What's really important for you, the only thing you really need to know is the middle part that I just finished drawing, the molecular orbital part. You guys remember what I'm talking about when I say 2px, 2py, 2pz? Remember that the 3p atomic orbitals are all perpendicular to each other. If you impose a Cartesian coordinate system on them, on the atom, one is along the x-axis, one along the y-axis, and one along the z-axis. That's what those are. Do you see what I'm showing here? The 2px, 2py mixed together, they make the 2pi, 2p. These are bonding, but pi bonding molecular orbitals as opposed to what we call sigma. And also the pi star, the pi anti-bonding 2p molecular orbitals. And then the 2pz's combine to make sigma 2p, sigma star 2p. So it looks more complicated now, right? But like I said, this middle part is the important part for you to know. And this diagram right here, actually I'm going to rewrite that over here. So. If the atoms involved in the molecule are in the second row from lithium through nitrogen, then this is the order of the molecule. This is the molecular orbital energy level diagram that you use. If one or more of the atoms is oxygen, fluorine, or neon, then what happens is the sigma 2p and the pi 2p switch places. And it looks like this. Because we're only talking about diatomics here, what I'm saying is if one of the atoms or both of the atoms is oxygen, fluorine, neon, use this. Now, that rule that I just gave you here is slightly different than the one that they give you in the textbook. I want you to use what I say, okay? Obviously, we're always saying, right? What they tell you in the book, just so you know, is that this is what you use if the atoms are within one in the periodic table of each other, right? No more than one block away. And then they don't tell you what to use if it's more than that, right? do it this way. This will be good for us. That's different scales. I should have ended at the same place. Don't get thrown off because this went higher than this. That's just because I can't draw. They're supposed to be the same. Okay, so far? Now here's how you use them, right? And we'll be finished with molecular orbital theory for now. All you do is, for a given molecule, and again, remember, we're only doing really simple diatomic molecules, first or second run. You count up the total number of electrons for both atoms, fill in it, just using the same rules. Once you do that, then what you can do are the same things we've done so far. You can calculate the bond order and talk about the length and the strength of the bond. You can predict whether or not that molecule is paramagnetic or diamagnetic. For example, dilithium, right? How many electrons? Now remember here, we're counting all the electrons, not the valence electrons. If you use the picture like I'm showing you with the sigma 1s, sigma star 1s, right? How many electrons total in dilithium? 6, right? Which picture do we use? One on the left. So we start putting electrons in, right? So this is for nitrogen.
Yeah.
1, 2, 3, 4, 5, 6, right? You guys see that okay? What's the bond order? No, it's not 0. I know, maybe I do these a little too close. These two are in a bonding, these two are in an anti-bonding, and these two are in a bonding. 1, right? So again, the way you do it is count up the total number of electrons in bonding molecular orbitals. Can you guys see that these two and these two are both in bonding molecular orbitals? So we have 4 bonding electrons. We have 2 anti-bonding electrons. So we have 4 minus 2 over 2, which is 1. Okay? Is the molecule paramagnetic or is it predicted to be paramagnetic or diamagnetic? Diamagnetic. And that's the kind of things you do. Another thing that you can do, or you can compare based on the bond order, you can compare the length and strength of bonds in different molecules. The higher the bond order, I'll write this down in a second. The higher the bond order, the shorter and stronger the bond. The lower the bond order, the longer and weaker the bond. So let's try fluorine, the molecular fluorine. Because it's fluorine, we're going to use this diagram, not that one, right? We'll just fill it in. How many electrons total in a fluorine molecule? Good, 18, right? Got it. So we start filling them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So, what's the bond order?
0.
Is it? I don't think so. Okay, so don't, at least at first, don't take shortcuts. Just count up the bonding electrons just real quick. Count up the antibonding electrons, subtracting divided by 2. So first, how many bonding electrons do you guys see here? 10, right? You guys agree? 2, 4, 6, 8, 10, right? And how many antibodies? 2, 4, 6, 8, right?
Yep.
So bond order of 1. We know fluorine, it's one of the molecular elements, right? Diatomic elements. We kind of knew that already. Paramagnetic or diamagnetic? Diamagnetic. So you guys getting the idea?
Yeah.
So that's all there is to it, right? So make sure you know the two diagrams. Before I go on to the next topic, let's do a heteronuclear diatomic. These are homonuclear because of both the same atoms in the molecule, right? What about this molecule right here? Which diagram should we use? The left or the right? Right. And the reason is because at least one of the atoms is either oxygen, fluorine, or neon. Again, your book doesn't tell you that rule. That's the rule that I'm asking you to use. How many total electrons? How many? 15, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. 14, 15. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. So Bond order? Okay, so how many bonding electrons?
10.
Anti-bonding? 5. 2, 4, 5, right?
Yeah.
To 2.5. So what does that mean? It means that it's shorter and stronger than a double bond would be, but longer and weaker than a triple bond would be. Half of the two. But the molecule is predicted to exist. That's nitrogen monoxide. I mean, it's a strange molecule, but it exists, right? Paramagnetic or diamagnetic? Good. One more, and then one more. We always have to do, because we kind of brag about, or not really brag about, but explain why we even have, one of the reasons why we even have molecular orbital theory, why we have to do it. It ends up that the molecular oxygen, O2, they probably have a picture in your book somewhere, they have it in most books, of we take liquid nitrogen and you pour it between the poles of a magnet. It's held there, right? And the only way that can happen is if it's a paramagnetic species, right, O2. The Lewis structure has all the electrons paired up, right? The Lewis structure for oxygen is like, you guys know. Everything's paired up, right? So this predicts that it's going to be diamagnetic, and it should just go right through that magnet. Did you guys find that picture? It's always, yeah, there it is. Page 277. It's cool. So we just filled it in. How many electrons in an oxygen molecule? 16, right? We got 15 here, so just one more, right? Like that. So you can see that we have 2 unpaired electrons. It makes it paramagnetic, which it is. What's the bond order? I think it's going to be 2, right? But, okay. Bonding electrons, we have 2, 4, 6, 8, 10 still. Anti-bonding, we have 2, 4, 6, right? 1, 2 equals 2. So we get a double bond just like we do in Lewis theory, but we also get that it's paramagnetic instead of diamagnetic, which we know it is because of that picture. Okay. Well, okay, so that question?
Yeah, that second, this one, prepares for which elements?
Oh, okay. Okay, yeah, that's important to make sure you get that. This molecular orbital energy level diagram, this order, and the only difference are the relative positions of the sigma 2p and the pi 2p. They switch places. This molecular orbital energy level diagram is if both of the elements are lithium through, actually hydrogen through nitrogen. It's just hydrogen and helium, just use the bottom two, right? But it'd be hydrogen through nitrogen. If at least one of the elements is oxygen, fluorine, or neon, then use this picture. And over here, where it said memorize figure 9.13, that's this one plus other, that's the other. Okay? Just so they, a little look ahead. molecular orbital theory applies to not just diatomics, not just second rows. It applies to, you know, any molecule, right? Thing is that anything past second row diatomic, it's more complicated than we want to deal with here. And the way we deal with it, when you get to organic chemistry, you'll deal with it. But luckily, you won't have to do any of the actual calculations or memorize any of these yourself. What you do is you have a computer approximate the solution to Schrodinger's equation, and you can get molecular orbitals from that. And when you get that, it'll give you really good pictures of what the molecular orbitals look like. And one of the things that you can use those molecular orbitals for is the computer, the program, Schrodinger's equation, will tell you which molecular orbital in a given molecule is the lowest unoccupied molecular orbital, the lowest energy molecular orbital that doesn't have any electrons in it. That's the one that's going to be able to accept electrons from another molecule and make a bond, right? And it's also going to tell you what the highest occupied molecular orbital is. That's the molecular orbital that's the highest energy that has electrons in it, like the valence electrons. Those are the electrons that are most likely to react and form a bond to another molecule. So when you get these pictures, then they're all different shapes. And you see where the highest occupied molecular orbital is on this one and the lowest unoccupied molecular orbital is on this molecule. One way of predicting where they're going to react, where they're going to form a bond to make a new molecule is the highest occupied on this with the lowest unoccupied on that. That's kind of where this gets to later on. But for now, through the second row of diatomics, and that's it. Okay? All right. So that's molecular orbital theory. A different bonding theory, is called hybridization theory. And that's what we're going to talk about now. Before I explain the mechanics of what you're going to have to do to use hybridization theory, let me explain why, the reasoning behind why we need it, why we talk about it. We try to explain how bonds form in molecules. Take method, stage 4. Carbon atom, 4 hydrogens. If we look at where the valence electrons are in each of these atoms before they form any bonds, each hydrogen atom comes with 1 electron and it's in a 1s orbital, which is a sphere. There's 1 electron there. The carbon has how many valence electrons? 4, right? And so its electron configuration is helium 2s2, 2p2. You guys agree with that? So those are the 4 electrons. There's a 2s, has 2 electrons, and it has 3 2p orbitals. So you kind of have to watch as I draw this. It gets kind of complicated. That's one of the 2p's. Okay. That would be another 2p. The third 2p would be coming out of the board towards you and going back into the board. Picture that? And we have one electron here and one electron here. So one of the things that we know about methane, CH4, is its shape. The Lewis structure looks like this. What does Vesper theory predict the molecular geometry to be?
Tetrahedral.
Tetrahedral, which means that the bond angles are all the same and they're all 109.5 degrees. Here, okay, using just the valence bonds, okay, when we form a bond, valence orbitals form bonds, is by overlapping atomic orbitals. A 1s here, say with a 2p here. So there's one electron here and one electron here. Okay, that can form a bond because there's two electrons. And there's an orbital overlap. Right? You guys understand kind of what we're making these bonds. So that would be one of the carbon-hydrogen bonds. And the same thing up here. That's two of them. Now we have two more bonds to form, right? Because we know it has 4 bonds in every tetrahedron. The 2s orbital has 2 electrons in it. It can't form any more bonds, right? The other 2p orbital doesn't have any electrons in it. It can't form any bonds. Each of these has 1 electron just like those two. And on top of that, the 2 bonds that we can show forming with this method, what's the angle between them?
90 degrees.
90 degrees. And we know that's not true either. Okay? The next logical thing to do would be to say, well, what if we had an excited state in carbon? What if we took one of these 2s electrons and we gave it just enough energy to kick up into the other 2p orbital? Okay? Then we could form a bond with this 2p and a hydrogen 1s, with this 2p and a hydrogen 1s, and with this 2p and a hydrogen 1s. Are you guys following? I can't draw that third one. Can you imagine it? And we could also form, I guess, a bond between a hydrogen 1s and the carbon 2s, because now it only has 1 electron. So we can get 4 bonds, but the problem is the shape. It's the geometry. 3 of those bonds are going to be 90 degrees to each other. We know that's not true. And the 4th bond, there's no telling where that's going to be. It's going to have to fit in there somewhere, and it's going to make a bond angle of even less than 90. Okay? So this doesn't work. We can't explain what we know to be true, and that is that carbon is a tetrahedral molecule with 4 equivalent bonds, all 109.5 degrees from each other. So what we do is we mix together the atomic orbitals on carbon. We only do this for the central atom. So we have a carbon, we have 2s, and we have 3 2p's. We combine them together, we get our, what we call hybrid orbitals. Hybrid orbitals are kind of like mules, right? Donkey and a horse. Right? It's not a donkey and it's not a horse, it's a mule, right? It's a hybrid. So we get 4. The thing is, we start with 3 atomic orbitals here. No, 4, what am I saying? And we end up with 4 atomic, localized, but hybridized orbitals. There's better pictures in your textbooks, but it looks something like that. There. These orbitals are called sp3. There's a picture on page 284 of an sp3 orbital. We started with 4 orbitals, we end up with 4 orbitals. The difference is these 4 hybrid orbitals, these 4 sp3 orbitals, are exactly the same as each other, and they're all pointing 109.5 degrees away from each other, and they form a tetrahedron. They're all localized, they're all centralized on that carbon atom. And they point to the points of a tetrahedron. The picture, the same page, 284, there's a picture of it. So once we do that, we can describe this way. In this picture, again, energy is increasing up. 2s, an electron in a 2s orbital is lower in energy than an electron in a 2p orbital. 2p's are the same as each other. When we combine these 4 orbitals, making 4 hybrid orbitals, the 4 sp3 hybrid orbitals are higher in energy than the 2s, but lower than the 2p's. If this is carbon, then it's 2s2, 2p2. Again, the arrows mean the same thing. They represent electrons. What we do is we imagine those 4 orbitals combining to make the hybrid orbitals, and now take those 4 electrons and putting them into the hybrid orbital. So now what we have 4 equivalent sp3 orbitals, all 109.5 degrees from each other, forming a tetrahedron, each with 1 electron. So now we can form 4 bonds to hydrogen atoms. And those bonds are going to be 109.5 degrees from each other, right? They're all going to be the same as each other, just like in methane, right? Guys, that's buying that? Well, no, not really.
What happens when you fill up like all the sp3, you have excess electrons?
Well, how many electrons would that be?
Like 8?
8. What's the most you can have over here?
8?
So you're not going to be able to overfill it.
Well, I'm really like go past. You can't go past that.
Yeah, you can. You can do these. But again, every time you make a new hybrid orbital, you have a new unhybrid orbital, right? So it's, the number of orbitals is conserved, which means you can't ever possibly overfill. Right? good place to stop today. What I'll do next Monday